Well, here we are. We made it to the final chapter. So this is the final chapter that this course covers, and it's going to be about acids and bases. And to understand this very important concept, this is one that translates 100% into biology courses that you will be taking in the future. To understand that, let's cover these topics. So the first thing we're going to have to understand what an acid is, and we're going to see that there's several definitions, and these definitions are like such because through the years, or actually through the centuries, as we discover more substances that behave like acid and bases, we see that the previous definition doesn't work. So we have been creating new definitions that explain the behavior of acid and bases as we discover new substances. So you're going to have the Arrhenius, you're going to have the Bronsted, and you're also going to have the Lewis acid, which we don't cover on this course. Then we will briefly talk about characteristics of acids, and I can tell you right that now because I'm not going to cover it really. Acids are going to be sour, while bases are going to be kind of soapy and chalky. So a lemon is very sour, so that's because you have a low, strong acidity. We're also going to see that acids react with bases, and we call those reactions neutralization reactions, where one cancels the other. And they also react with metals, and they also react with oxides, the acids. And we're going to see how we're going to write these chemical equations. Then you did this on chapter 12 already. We're going to revisit the stoichiometry of solutions, molarity, because we're going to measure the strength of acid and bases with molarity. And we're going to see that we can actually do a very precise reaction where we can find the end of the reactions by doing what we call a titration. But the math that is involved is what you did on chapter 13. And with that, we have to define what the strong and weak acids are. That's going to be really easy. And the same thing with the bases. And overall, we're going to see that this ion, this polyatomic ion, H3O+, is what defines an acid. So any substance that creates that will be an acid, and the more you create, the more acidic you are. The same go for the base, but with the OH, or the hydroxide. And we're going to see how we can always calculate one given the other. And then we're going to develop a scale based on the concentration of both of them. And the respective scales are going to be called the pH scale and the pOH scale, which are inverse to each other. So that's what we're going to be doing there. And we're going to close the chapter by talking about buffers. And buffers are very easy to understand, but super important. As important as if your buffer fails right now, you will be dead. Your blood has to be, doesn't matter what, your blood has to be somewhere between 6.8 to 7, somewhere in there. I don't remember exactly how much it is, but it cannot move from whatever range that is. And a buffer is what prevents your blood from changing pH. If it changes, you will be dead. So it's extremely important. So let's go ahead and begin by understanding what an acid is. Few things I want to tell you before we even go into this objective. To be an acid, you are going to have hydrogen. Your formula, 99% of the time, will begin with hydrogen. The hydrogen is going to be attached to something. However, to be an acid, it cannot be hydrogen attached to anything. Like a compound like this, it has a lot of hydrogen, but it's not an acid. It will have to be something like this, for example. And the reason is because as you know, the electronegativity of hydrogen is 2.1 from your electronegativity table, and bromine is going to be somewhere close to 2.7. I don't know it from memory, but as you know, the difference between these two is going to be more than 0.4, which means this is going to be a polar bond, which means the electrons are going to be closer to the bromine, and you can see that the hydrogen is going to be hanging by a thread on that analogy. And if you happen to put this, so this will be partially negative, partially positive, and if you happen to put this close to water, so most of the time an acid is going to have to be in an aqueous solution. So I would say all the time. And you know that water is partially negative, partially positive, and you're going to have more water surrounding that. This will start pulling on that hydrogen that is hanging by a thread, and it will break that bond, making water, but with a hydrogen attached to it, which is nothing more than H3O plus. So any substance that is capable of producing hydronium is going to be an acid. But to be an acid, it's going to have to be attached to something relatively electronegative so that the hydrogen is hanging by a thread in that analogy. So that's the first thing I want you to understand about acids. So with that said, let's explore two of the definitions for acids: Arrhenius acids and Bronsted-Lowry acids. And we will do the same thing with their base, and we will also know about a new concept, their conjugates. So let's do that by studying some problems. So identify each substance as an acid or a base. So I told you already, an acid is going to have hydrogen. Most likely, the formula is going to begin with a hydrogen. So let's do that. Let's stop right here. So let's find the acids. That would be an acid based on this. That would be an acid based on that, right? So if it's not an acid, then most likely it's going to be a base. So that would be a base, and that would be a base. So we got those two done already, just because of this fact. Most of the acid formulas are going to begin with a H. Write a chemical equation showing how it is an acid or a base according to the Arrhenius definition. For us to be that, we have to understand what the Arrhenius definition is. The Arrhenius definition tells us that acids produce H+, which is also known as a proton. And it's very interesting to know why we call this a proton, right? Hydrogen have atomic number 1, so one proton. There's no neutrons on hydrogen 1 because there's 0 neutrons. And because you have 1 proton, it's going to have 1 electron. So that would be H. So what would be H+? Well, H+ would be exactly the same thing without the electron. So what do you have left? You have a proton. That's what we call the ion H+, a proton. Because that's what it is. It's a proton. So also, according to the Arrhenius definition, bases produce hydroxide. So that's the Arrhenius definition. Acids produce protons, bases produce hydroxide. So let's go ahead and write the equation for the acid or the base according to the Arrhenius definition. So H2SO4 will produce H+ plus HSO4 negative. Notice that I begin with 2 hydrogens. So if I lose 1, I can only have 1 left. Notice that this is neutral. So if I lose positive, this better be negative, right? Because neutral is positive plus negative. It becomes 0. So that's how we will say that sulfuric acid, and you learn how to name the acids on the initial chapters of this course. Sulfuric acid will behave like an Arrhenius acid just that way. What about hydrobromic acid? Hydrobromic acid will behave as an Arrhenius acid by producing H plus and Br negative. So it's important that you keep track of those charges so it be the same charge on both sides altogether. What about the bases? Well, according to the Arrhenius definition, the bases produce hydroxide. And one thing, this is aqueous. So this is going to be aqueous. So all this happens in a solution that contains water. And as before, keep track of those charges. And you know how to do a backward crisscross to find out the charges of an ionic compound. Arrhenius bases are going to be ionic compounds, a metal with a non-metals. And then NaOH as a Arrhenius base will produce Na plus aqueous and hydroxide. So once more, Arrhenius bases produce hydroxide, Arrhenius acids produce protons. And that's how we're going to show with an equation that these are Arrhenius acid and bases. So what about the Bronsted-Lowry definition? Bronsted-Lowry definition came after the Arrhenius when we start seeing other substances that produce hydronium and were acids, but they didn't produce H+. So this one is different. So Arrhenius acid will donate H+, so which is the same thing as producing H+. So but now we are implying that something has to take it, while bases will accept H+. So the big change on the Bronsted-Lowry definition is that the base does not have to produce hydroxide anymore. As long as it can take the hydrogen from the acid, that's a base. That's how a base behaves. So let's do that again. Identify each substance as an acid. Oops. Or as a base. So once more, my acids are going to be easy. They begin with H. The bases, I cannot look for hydroxide anymore because this is the Bronsted-Lowry. They do not have hydroxide. They have to be able to accept a proton. So let me write the chemical equation to see if we can see it better. When we do Bronsted-Lowry, your chemical equation will always be plus water. So the Bronsted-Lowry chemical equation of an acid or base will have to include water. So let's do HBr. So HBr, which is aqueous, is going to be reacting with that water, the water that is part of the solution, right? And according to the Bronsted-Lowry definition, the acid will donate a proton to something else, so the water will take it, becoming plus, and the acid just donated a hydrogen, so it becomes Br negative. So what we see here is we have to have water so that the water becomes the acceptor. Therefore, the acid can donate. It doesn't have to produce, it just can donate the hydrogen or the proton to the water. So that will be the balanced chemical equation for hydrobromic acid behaving like an acid. What about nitric acid? Nitric acid, Bronsted-Lowry, so you have to have plus water. The water will take the proton, which means the acid donated that proton, so it doesn't have it anymore. And make sure you keep a track of the charges so that in this case, the left side is neutral, all combined, while the right side is also neutral because you got +1 and -1, so they cancel each other. What about the bases? The bases are the interesting ones. The bases are going to be the ones that, well, it was so easy to say this is produced hydroxide, so I can see it. Now we cannot say that. So once more, Bronsted-Lowry. So we're going to have to add water. And the base is supposed to take a proton according to the, accept a proton according to the Bronsted-Lowry. So the water can go both ways. So water is going to give off a proton. So if ammonia is a base, then it will gain a proton becoming plus because it just gained a positive hydrogen. And the water just lost the hydrogen producing hydroxide. And that's what tells us, oh, wow, this is a base. But it's not a base because it contains hydroxide. It's because a base because it was able to produce hydroxide indirectly. That's what we need, a new definition, and this is the Bronsted-Lowry definition. If you can show that this substance in the presence of water produces hydroxide, then this is a base. So C2H5 and aqueous Bronsted-Lowry, so make sure you add water to it. The base will accept a hydrogen becoming positive, and the water just lost a hydrogen. So here's our evidence that this is a base. It produced hydroxide. So that's how we do it with the Bronsted-Lowry definition. Water has to be one of the reactants, and water is either going to accept hydrogen if it's reacting with an acid, or it's going to accept, donate hydrogen if it's reacting with a base. The base will be the one accepting the hydrogen. So with that said, it's time for you to practice. So you are going to do, we're going to start with the Arrhenius definition. So make sure you do what you know how to do. And after you do that, then you're going to do the same thing with the Bronsted-Lowry definition. Refer back to this recording if you need to fine-tune your knowledge on that. Once you do that, now we're going to do something different. For each reaction, identify the Bronsted-Lowry acid. So the Bronsted-Lowry is the one that donates a proton. The Bronsted-Lowry base, the one that accepts the proton. And identify the conjugate acid and the conjugate base. So conjugate, like on a marriage, is the one that is always with you. And what does that mean? That means that if I have an acid will donate or lose a proton, and what remains is that, right? So this would be my acid, and whatever remains is going to be my conjugate base. If I have a base, bases accept protons, so this will become NH4 plus. So this will be my base, and this will be my conjugate acid. So you can summarize that by saying a base always produces a conjugate acid, and acid always produces a conjugate base. And since you know that the acid loses the hydrogen, whatever remains is the conjugate base. Since you know that the base gains a hydrogen or a proton, whatever you make is your conjugate acid. So with that in mind, let's do this problem here. So let's find on this reaction. So on this reaction, this will be my acid, and my acid is losing a hydrogen, becoming that. So that would be my acid, and this would be my conjugate base. So the HBr as an acid lost a proton. Whatever remains is my conjugate base. That's what I just did. So that means for the acid to lose a proton, the water will have to take it. So that's my base. And once the water takes the proton, it's going to make this. So this will be my base, and this will be my conjugate acid. What about the next one? The NH3 is becoming NH4. So that means it's gaining a proton. So therefore, this has to be my base because it's gaining a proton. Therefore, the water is becoming hydroxide, which means it's losing a proton. Therefore, this would have to be my acid, and this will have to be my conjugate base. So by following the arrow, the base produces the conjugate acid. By following the other arrow, the water produces the hydroxide. Since water is losing a hydrogen, that's the acid, and the hydroxide will have to be my conjugate base. So that's a good way of doing it. Kind of find out what's becoming what and see what's happening, label it, and then you know how to label the other one. So let's do this one. The HNO3 is becoming nitrate, so that means it's losing a proton. So that's the definition of an acid. So if this is the acid, this is the conjugate base, always the opposite. The water is taking a hydrogen, or a proton, better said. So that means this is my base, and this is my conjugate acid. And the last problem, the C2H5 or ethyl amine C2H5N is becoming C2H5N plus. So that means it's gaining a proton. So this has to be a base because it's gaining a proton. And this has to be my conjugate acid. The same way, water is becoming hydroxide. So the same way, water is becoming hydroxide, like I said, which means it's losing a proton. So therefore, this is my acid, and this has to be my conjugate base. So that's how we find out which is with using what you learned earlier about identifying acid and bases. So go ahead and work on these 3 problems. Something I need to bring up to your attention is, well, let me show you here, that sometimes you're going to see 1 arrow, other times you see 2 arrows. The 2 arrows means that there's an equilibrium established. We don't cover equilibrium on this chapter. It will actually be chapter 15, which is the chemistry 1407. So what equilibrium means that at all times they're going to be going back and forward. So at all times you're going to have everything present on your flask. The strong arrow means that the products totally become, the reactants totally become the products. So at the end, your reactants are totally gone. So it's important to understand the last lecture on this chapter, but it's a whole chapter on that we are not going to get to cover. Belongs to another course. So go ahead and do 14.3. And once you do that, you already have practice on this, so let's do this real quick. Write the formula for the conjugate base of each acid. So all of these are acid. How do I know that? All of them begin with hydrogen. So all acids are going to lose a proton. We donate or produce. So both Arrhenius and Bronsted-Lowry definitions apply. And all you have to do is subtract the hydrogen that you just lost and keep track of the charges. Since the beginning compounds are neutral and they're losing 1 positive, they have to become negative. And just like that, we wrote all the conjugate bases because these were my acids. So you're ready to do that, to reinforce that concept. And when you're done with that, let's do something else. So you can do the conjugate base given the acid. Can you do the acid given the conjugate acid given the base? So let's see. According to the Bronsted-Lowry definition, bases accept protons. So all of them will accept a proton, or a proton will be added to it. That means you're just going to add H plus to it. So plus negative makes it neutral. So the Cl negative is the charge doesn't show. The HSO3 or hydrogen sulfide is gaining a hydrogen. So there's going to be 2 of them now. Actually, this is wrong, sorry. This should be 3 there and minus 1 there. So that becomes neutral then. Same here, sorry. I don't know what happened here. There should be 2 of them and negative there. So this will gain a hydrogen and becomes CHO2. And the NH3 gains a hydrogen and becomes NH4 plus. Keep track of the charges. Begins neutral, gains a positive, so it's going to have to be positive at the end. So we just did all our conjugate acids because we were beginning with bases. So now you're ready to do that. Let me make sure there's no typos in here. Yeah, I don't see any typos. And once you do that, we are done with this first lecture of our last chapter. Now you understand what the Arrhenius acids are. They produce H+. Bases produce hydroxide. While the Bronsted-Lowry acids donate a proton, so they lose a proton, and the bases gain a proton. And we learn about what the conjugate is. So whatever If an acid loses a hydrogen, whatever remains, that's your conjugate base. If a base gains a proton, whatever you form is your conjugate acid. So once you do that, like I said, we're done with this part of the lecture. And when we come back, we will go into different types of acid-base reactions, neutralization reactions, also reaction of acid with metals and metal oxides. So until the next time, see you soon.